Dear students, in physics, we are going to start the first experiment. You know, the first section you have in physics is about measuring instruments, right? So, we have few measuring instruments that we have to familiarize with in this section, right? First measuring instrument that I have taken to show you is the vernier caliper, right? Vernier caliper is one fundamental measuring instrument you have in your laboratories. You will not have it at home, right? You have it at laboratories. So, first let's see what a vernier caliper is, what are the parts in it, how we do measurements, what kind of errors are possible. You know, we have to familiarize all of them. So, let's look at the theoretical background or like bit of a learning about all these vernier caliper related matters, and then we will go into the practical or the experiment using the vernier caliper. Clear? Right. So, see vernier calipers. This is how the vernier caliper will look like, right? When I start the experiment, you will see that. These two parts you call inside jaws or internal jaws. These two you call external jaws. So, what happens is, now this part is movable. You can move this. You can move it, right? The main scale, something like a meter ruler. You can see that here. Like a meter ruler, you have the main scale. Usually, it will be there up to 14, 15 centimeters is the usual vernier caliper's length. 15 centimeter, around that. And then this vernier, that has another scale in it, which is slightly different to the main scale. We will look at that later. So, we call this scale as vernier scale. This is main scale, like the long one, lengthier one is main scale. The short one is vernier scale. Vernier scale is movable. When you move that, the jaws also will move. See, this side will be fixed. This will be fixed. These two are movable. So, when you move the vernier, these two jaws will move. And then we have to, use this scale and get the readings. That's what we had learned now, how to get the reading. This is how we keep. See, you measure the diameter of this sphere. Then you keep the sphere here, close it, and we get the readings. When we do the experiment, you will understand that well. Sometimes you may have digital vernier calipers, where you don't have to, like calculate and read and everything. You will have everything shown there. It's like this. Clocks or watches, if you take the wristwatch or wall clock, the traditional way you see the clock is there will be like different scales 1 to 12 and like different arms. So, you read the time based on that. See, if it is like if the short arm is in between 2 and 3 and the long arm is at 5, then you say it's 2:25. So, we learned how to read time based on that. Similarly, there are digital watches as well, where like the time in numbers it shows. You don't have to calculate anything, like you just read the numbers. Similarly, vernier scale also, the traditional method is this. This is what you will find in the laboratories mostly, but nowadays you have this one as well, right? Let's see all this, like when we do the experiment, we will see how we are going to read. So, usage of vernier calipers, there are 4 things that we are going to measure in this experiment. Finding the volume of block of wood. We will take a rectangular block of wood, a cubic wood, and we will find the volume of it. How to find the volume? So, if it is a cubic like rectangular wood, then you need the length, width and height. Length, width and height, those 3 will be required. Finding the volume of the material of a PVC tube. When you say PVC tube, that's how it's going to be. Yes. So, we may have to measure the internal diameter, external diameter and then length. You need all of them, right? So, how to measure them? Internal diameter, external diameter. Finding the volume of the material of a solid sphere. Solid sphere. Right? Solid sphere. How do we measure the solid sphere's volume? It has to be 4 by 3 pi r cubed. So, as long as you can measure the diameter, diameter by 2 is going to be the radius. Pi r 4 by 3 pi r cube you can apply. Finding the internal volume of a hollow cylinder. PVC tube and hollow cylinder are going to be similar. But then PVC tube will not have a base. Hollow cylinder will have a base also. I will explain when we come into those. I will explain how to find them. Let's first understand the basics of vernier caliper. If n divisions of vernier caliper's main scale are divided into n divisions of vernier scale. I will explain that. Listen. Now let's say this is the main scale. Main scale is, let's say, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say this is 1 centimeter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 1 centimeter. That means each division here is 1 millimeter. Each division is 1 millimeter. Now this is the main scale. Now let me show you the vernier scale. Let's say when the 0 and 0 are aligned, when zeros are together, vernier scale will be usually a little bit smaller than the main scale. Now look at this. Let's count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what you see here, 10 scales of vernier divisions match with 9 scales of main division. Do you see? 0, 0 were together and the last line is together, but that is the 9 scale of main division. So can I write like this? Look at this. 10 vernier scales are equal to 9 main scale divisions. Main scale divisions each is 1 millimeter, so 9 millimeter. That means one vernier scale division is 9 by 10, which is 0.9 millimeter. 0.9 millimeter. 9 by 10, 0.9 millimeter. So n divisions of vernier scale is equal to n divisions of main scale. One division of vernier scale will be n by n. That's what I have done. This is capital N, this is simple n, divided that many divisions of main scale. The difference between one division of vernier scale and one division of main scale is known as the least count. So least count means, actually, like if you look at here, least count, how we define least count is one division of main scale, one division of vernier scale difference. Basically this difference. Can you see the difference here? So one division of main scale is 1 millimeter. One division of vernier scale is 0.9 millimeter according to what I have shown here, 0.9 millimeter. So 1 millimeter minus 0.9 millimeter, 0.1 millimeter will be the least count of this vernier scale. Least count, right? Least count is 1 minus n over n main divisions. Commonly n is 9, n is 10, therefore least count will be 0.1 of the main scale division, 0.1 millimeter. Where did I get millimeter from? One main scale was 1 millimeter, right? So 0.1 of that main scale division, 0.1 millimeter. This is how we decide the least count. Least count means what? Look at this. If you take a clock, right, the seconds that move second by second, one by one, right? So the lowest time, that smallest time we can measure using a wall clock is 1 second. Anything smaller than 1 second you can't measure there, right? It moves 1 second. Tick, 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 tick. Every tick is a second. So can I measure half a second there? No. Wall clock doesn't give you half a second. Therefore I can say least count of a wall clock is 1 second. If you take a meter ruler, you will have centimeters and each centimeter would have been divided into 10. That means 1 millimeter. So whatever the measurement you take has to be in millimeters only. Whole numbers are millimeters only. Half a millimeter, 0.2 millimeter, 0.3 millimeter, I can't measure on that. Understand? So least count means the smallest measurement that we can take using an instrument is what you call least count. Smallest measurement that you can take from a measuring instrument, right? Let's say, okay, I'll tell you in terms of money. Let's say I have I'm living in a country, let's assume I'm living in a country where the smallest coin we have, smallest value of a coin we have is 1 rupee. There is nothing less than 1 rupee. Then all the prices you pay has to be in whole numbers of rupee, right? 28.25 rupees you can't pay. Why? You can either pay 28 rupee or you can pay 29 rupee. 28.25 you cannot pay because you have all 1 rupees. Imagine a country which has only 10 rupee coins. 10 rupees is the smallest value of coin they have. There is nothing less than 10 rupee. Then the prices of all the products have to be 10 rupees multiples. You can't pay 27 rupee. You can either pay 20 or 30, not 27. Do you understand? So, least counts multiples only the values will be possible. If you say least count is 0.1 millimeter, from this instrument, whatever the reading you take has to be 0.1 millimeters multiples. You can say 25.7 millimeter. Correct. 25.72 millimeter? No. 25.72, how did you get? You can't, because 0.1 is the least count. 0.02. When you say 25.72, how did you get that 2? You can't. That is a division of 0.1 millimeter. So you can't take that. So understand, when they define the least count of a measuring instrument, the measurements we take from that measuring instrument has to be multiples of that least count only. Anything smaller than that least count is not measurable. Not measurable using that measuring instrument. You can find another measuring instrument with more accuracy. For example, what we can measure with wall clock, you can take a stopwatch and measure it. Stopwatch can measure less than 1 second also. Each second it measures into 100 divisions. Each second it measures into 100 divisions. So, one out of 100 of a division can be measured, of a second can be measured. But wall clock we can't. Right. So, this vernier caliper can measure only up to 0.1 millimeter. That's the usual vernier caliper. There are vernier calipers with different accuracy. I'll show you how it is possible. Look at this. Think I have a vernier caliper, main scale each is 0.5 millimeter, 0.5 millimeter, and they have made 9 main scales, 10 verniers. So I can say 10 vernier is 9 into 0.5 millimeter, 4.5 millimeter, correct? Correct? 0.5 millimeter, 9. So, one vernier has to be 0.45 millimeter. Least count has to be one main scale minus one vernier scale, right? One main scale is 0.5 millimeter. One vernier scale is 0.45 millimeter. 0.05 millimeter. See? Earlier we had only 0.1 millimeter. Now the least count has become smaller. When the least count becomes smaller and smaller, accuracy increases. Accuracy increases. So this is a better vernier caliper than the previous one. How did I improve the accuracy? How did I reduce the least count? I have divided the main scale again into 2. Earlier we had main scales only 1 millimeter, 1 millimeter. This time I have main scale 0.5 millimeter, 0.5 millimeter. Right? Another one. Look at this. One main scale 0.1 millimeter. Right? They have 20 verniers matching with 19 main scales. How about that? 19 into 0.1. So, one vernier will be 19 into 0.1 over 20. 1.9 by 20. How much is that? 1.9 by 20 means 0.95, correct? No, main scale we will take it as 1 millimeter, not 0.1. 1 millimeter. So, this is going to be 0.95 millimeter. So, least count has to be one main scale minus one vernier scale, 0.05 millimeter. Understand? Understand? Sometimes you may have this case also. Look at this. Look at this. One main scale is 0.5 millimeter, right? They say 50 vernier is 99 main scale. Now see, it's almost doubled, right? So when you calculate least count, there is a small adjustment. I will come to that. Earlier it was like 9 and 10 divisions, 49 and 50 divisions, 19 and 20 divisions. Numbers were very close. Now verniers divisions and main scales divisions, what they are matching, there is a double, like 50 vernier is equal to 99 main scale. No worries. Let's find the vernier scale. So 50 vernier is going to be 99 into 0.5. So 1 vernier is going to be 99 into 0.5 divided by 50. So it's 100.99 millimeter. So here you can't take 1 main minus 1 vernier. Least count is going to be 2 main scale minus 1 vernier scale. 2 main scale means 0.5 into 2 millimeters. This is 0.99. 1.01. I'll tell you why. Look at this. Let's say this is 0 main scale. This is the first one. This is the second one, main scale. Right? Vernier scale, 0, 0, okay, aligned. First one is going to be here because vernier scale is much bigger than the main scale because 50 verniers are matching with 99 main scale. So in this case, what we are going to define as least count is the gap between these two. Look at that. Because what we mean measure by least count is the smallest gap between a main scale division and the vernier scale division. Technically, that is what we call least count. Smallest gap between a main division and a vernier division. So the smallest gap comes not to the other side, it's here. That is basically 2 main scales division minus 1 main vernier scale division. This is 2 into 0.5 millimeter. This is 0.99 millimeter. Understand? So first step is whenever you get a vernier caliper, finding the least count. How do you find the least count? You first find how much is 1 main scale division is, what's the length of 1 main scale division. Then find 1 vernier scale division, right? If they are almost close to each other, 1 millimeter, 0.9 millimeter, then you get the difference between them. But if they are close to the multiples of each other, like this case, see 50 and 100, or 0.99, 0.5, it's almost double, right? Then you have to take double the main scale and subtract the vernier scale, right? Be clear with these. Next method. First find the least count of the instrument, whichever the measuring instrument you use. Now we are talking about vernier caliper, later we will be talking about micrometer, screw gauge, later we will be talking about spherometer. Whichever the case it is, first thing you have to do is to measure the least count of that instrument. Measure the least count. Then find the zero error if exists. What is the meaning of zero error? Zero error means, I'll show you, look at this. Here. When the fixed jaw and movable jaw are in contact. Now look at this. If you look at the instrument, right, you had one like this, say this is the scale, you had one jaw like this. The other jaw was movable with the scale. When you bring that movable scale and fix it here, right, can you see both jaws are in contact? This is the fixed jaw, this is the movable jaw, there is no gap in between. So when you come and close it here, how it should look like is main scale 0, vernier 0 must become collinear. They must be aligned. Both zeros must be in the same line. Look at this diagram. Both zeros are in the same line. If we get like this, there is no zero error. Right? When it is fully closed, when the jaws are fully closed, zeros are aligned, zeros are collinear, main scales 0, verniers 0 are in the same line, then you can say there is no zero error. But sometimes due to inaccuracy due to an error in the instrument, it's an error completely, it's an error. due to an error in the instrument, the zeros may not be aligned. Sometimes the 0 might be on the right side, sometimes the 0 might be on the left side. 0 can be different. It is something like this, I will tell you what. You might have seen the weighing scale, electronic weighing scale when you go to supermarkets or when you go to a vegetable shop. Nowadays people have this electronic weighing scale. You put the item on the scale, it shows you a number, this many grams. This electronic scale should show 0 when there is nothing kept on it. When you don't keep anything on its plate, it has to show 0 reading, right? It must show 0.00 grams. Sometimes, due to an error, even when we don't keep anything on it, it might show you a small weight. It might say 5 grams. Or sometimes it might show minus 5 grams. Even minus is sometimes showing. But electronic scale, it's very easy. You just press a button, it makes it 0. It adjusts it. But here we can't press any button. So we need to find a mechanism. Okay, if there is an error, how do we rectify the error after getting the reading? Right. So understand, there can be 0 errors. 0 error means what? Like in the weighing scale, even before I keep anything to be weighed, it shows you a reading, which is error. Similarly, here also, there is nothing in between the jaws. Jaws are fully closed, jaws are in contact, but still it shows you a reading. Clear? Right. So, look at this. We have defined 2 types of 0 errors, positive 0 error and negative 0 error. Positive 0 error and negative 0 error. Positive 0 error means, look at this, I'll draw a bigger diagram for you to understand. Say this is 0, main scale, this is main. 1, 2, 3, likewise it goes. Now the zeros have to be aligned, but the vernier scale 0 is a little bit on this side. 0, 1, 2, 3. And then if you look at the fourth one, 4, 4. So what is the error here? 0 and 0 has to be aligned, but 0, now the vernier 0 is a little bit on that side, So the error, what we call as error here, is this gap. This gap is the error. That gap is the error. How do we measure that error? Look at this. How do we measure that error? Very simple. Look at this. This is 3 main scale divisions. This is 3 vernier scale divisions. Here it's aligned, right? So error is 3 main scale minus 3 vernier scale. 3 main scale means 3 into 1 millimeter. 3 vernier scale means 3 into 0.9 millimeter. 3 millimeter, 2.7 millimeter, 0.3 millimeter error is there. Right? That is the side vernier scale is moving, right? So on the positive side, that's the side vernier is going to move. When I keep some item in between the jaws, vernier has to be moved on that side, not on this side. Because scale is there on that side. So vernier will be moving on that side. So on the side when vernier is moving, you have an error of 0.03 or 0.3 millimeter. We call it positive error. Right? Suppose if I have it on the other side, it's going to be negative error. How do we adjust this? Listen, concentrate. Going back to the electronic scale example, think I have an electronic scale which shows 5 grams when there was nothing. Empty plate, it shows 5 grams. Then I kept something on it, right? Now it shows 90 grams. Tell me, what is the actual weight of what I kept on it? Let's say I kept some vegetables on it, or I put some sugar on it, right? It was already at 5 gram. After I put couple of spoons of sugar on it, it shows 90 gram, 90. So how much of sugar actually I have kept there? From 5 it has gone to 90 means 85 gram must be the actual weight of sugar that I have kept there. But the reading is 90. Reading is 90. So how it works is the actual value, actual value must be the reading minus error. Reading minus error. Reading you got 90 gram, but it actually started from 5 and it came to 90. So that first 5 I have to subtract it. So 85 gram is the correct value of sugar I kept on the plate, weighing scale. Clear? Same here. Suppose if this shows you a reading of 125 millimeter, it did not start from 0 to go to 125 millimeter. It started from 0.3 and went to 125 millimeter. So the correct reading of what I have read there, the correct length of what I have read there is 125 millimeter minus this 0.3 millimeter. Do you follow with me? Length minus error, or the reading minus error is the correct value of length. Reading minus error. Clear? Right. So reading minus error. Also I found the error like this, right? Fundamentals. But another method for you, you found which vernier division is getting aligned with the main scale. Third one, so you can say error is 3 into least count. Least count 0.1 millimeter, 3 into 0.1, 0.3 millimeter. How that works is, listen. Here both are aligned. This is where the first difference is. So this will have 0.1 millimeter difference. This is the second difference. So one and another one added. So this will have 0.2 millimeter difference. This is the third gap. So third gap has to have 3 into least count, 0.3 millimeter difference. Right? So simply you can find the vernier division. Which vernier division matches with main scale division? Third division matches there. So 3 into the least count will give you the error. This is positive error. Let's see negative error. Negative error. Look at this. Look at this. Like this diagram, I am drawing it bigger. All right. 0, 1, 2, 3, 4, 5, 6, likewise it goes on. This is main scale. Now the vernier, look at this. 0 has come to the other side. 0, 1, 2, 3, 4, 5, 6, 7. Likewise it goes on. So can you see 6th line of the vernier has aligned with main scale. 6th line of the vernier has aligned. So how much is the error? Error, this much is the error. But can you see 0 of the vernier has come to the opposite side, not to the side where it is supposed to move. Since it is in the opposite side, we call it negative error, minus error. Anyway, E. How do I find the E? Can you see 6 vernier divisions minus 5 main divisions. 6 vernier divisions minus 5 main divisions. 6 vernier means 6 into 0.9. 5 mains means 5 into 1. 1 millimeter each. Main divisions. Vernier divisions 0.9 millimeter. 5.4 minus 5, 0.4 millimeter is the error. This we call it negative error. So we have to actually write this as minus 0.4 millimeter would be an appropriate way of writing it. Minus 0.4 millimeter. How do we adjust this in the reading? Look at this. Come back to the weighing scale example. You have a weighing scale which shows minus 5 gram when nothing is kept. So it's at minus 5, not at 0, it's minus 5, below that. Say I got some reading, I kept something on it and it shows now 70 grams reading. Again, let's say I have put few spoonful of sugar on that. From minus 5 it has gone to 70. From minus 5 it has gone to 70 means how many grams I should have kept on that? Actually, I should have kept 75 grams because minus 5 has to come to 0. From 0 it has to go to 70. Minus 5 to 0, 5 grams. 0 to 70, another 70 grams. Altogether 75 grams. Even though your reading is 70, the correct value of what I have kept there is 75 grams. Right. So, with the reading, you had to add the value of error. 5 minus 5, the value of error is 5 gram, right? So, 70 was the reading, you added that 5 also and you said 75 gram as the reading, as the correct value of it. So, how do we adjust it here? Let's go with the same formula. Look at this. Value is going to be equal to reading minus error. Suppose this one shows me a reading of, let's say, 35 millimeter in this case, 35 millimeter minus, error is minus 0.4. See, so when you say negative error, if you are putting a negative sign, you can use the same formula, reading minus error, but this minus and minus will make it plus. Then this will become 35.4. Here different, if you get 60 millimeter reading and if the error is 0.3, 59.7 is the actual value. So look at these statements. Positive error will be subtracted from the reading. Negative error's value will be added to the reading. Value, not with the sign. Negative error's value will be added with the reading. Correct, because 60 has become 59.7 because that was a positive error. 35 has become 35.4 because it's a negative error. But if you are going to put the error with the sign itself, plus minus, negative error, if you put a minus sign, then you can always say reading minus error. If error is minus, that will automatically make it plus. Reading minus value plus. Right. So be careful about this. This is what we call zero error of the instrument. So the first step is to identify the zero error if you have any zero error. Let's go forward. Right. So now let's see how to find the volume of cubic block wood. So you know it's going to be a block like this, right? So we need to measure the thickness and then width or the length and the width. You need to take length, width, thickness. Then the volume will be length, width, thickness. So it's very easy what we do like this. See, you expand this, keep the block in the middle, right? If you want to measure the length, keep it in this direction and then close it. When you close it, can you see you have a screw here, right? Look at this. See, inside jaws, outside jaws. So you keep the block in between the outside jaws. Because we get the length or width between the outside. See, why I say outside is sometimes we'll have, okay, if you have something like this, you can use the inside jaws to measure the internal diameter. That's why you call it inside jaws. You can use the external jaws or outside jaws to measure the outside diameter, external diameter, right? So that's why we say external jaws or outside diameter, outside jaws. So keep the block in between outside jaws and you have this retainer. Can you see here? Retainer is kind of a screw, right? That's what we have shown here. Right, with this retainer or that screw, keep rolling it and then until it becomes, it touches, right? When it touches, then you get the reading. How do we get the reading? I'll show you how to get the reading as well. Let's say this is 2, 1, 2, 3, 4, 5. We'll take some space and draw it. Two, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 3. You know this is in centimeters. That means 2 centimeter, 3 centimeter means this is 2.1 centimeter. That means 21 millimeter, 22, 23, 24, 25, 26, 27, 28, 29, 30 millimeter. This is main scale. Now let's look at the vernier scale. Say vernier scale is like this. Let's say vernier scale is here. Right. Right. Let's say that's how the vernier scale is. Now look at this vernier scale. 0, 1, 2, 3, 4, 5. Fifth vernier scale is aligned with another division in the main scale. So the reading here will be, this is how you read it carefully. Look at it, concentrate. This is 2, 2.1, 2.0, 22. 22 millimeters finished here. After that only you get 0. Look at this point where 0 comes. So this is 22, right? Just before 0, what's the main scale? We have 22 millimeter. Just before vernier 0. Right before vernier 0. What is the last main scale division you have? 22 millimeters is the last main scale division you have. Then I need to get this much. How do you get that? Check which vernier division matches. Fifth vernier division coincides with the main scale division. Fifth main vernier scale division. 5 into least count 0.1. Since the fifth vernier division matches there, 5 into 0.1. 5 into 0.1. So that will give you altogether 22.5 millimeter as the reading. 22.5 millimeter. This is how you get the reading. Then after getting the reading, you have to adjust for the 0 error. You adjust for the 0 error. Right. Other thing, now when you are getting the measurement, usually we don't get the measurement at one place only. Say for example, if you are measuring the thickness, maybe you get the thickness at this point, then at this point, then at this point. Get the thickness at 2-3 different points. Usually we take it at 3 different points and we get the average. Because even though for the naked eyes it looks smooth, it looks uniform, actually the thickness may not be uniform. There might be slight variations in the thickness which we can't see with the naked eyes. So we take the measurement at multiple points and get the average for adjusting for all those thickness variations. Not only thickness, even the width, the length, all that we take at multiple points. We usually take at 3 different points, 3 different places you take it and get the average. Clear? Right. Then you do that for thickness, length and width. Multiply all of them. So get the readings, adjust for the 0 error. So adjusted readings, get the average. So average thickness, average length, average width, you have all 3, multiply, you will get volume. And usually questions on this will be connected to the density as well. So you know density is mass divided by volume. Mass divided by volume. You measure the mass of it. You can use the tri-beam balance. But if the weight is going to be less than 1 gram, if it is very small weight, then we can go for a chemical balance. Chemical balance or tri-beam balance, use it and find the mass. Volume you find like this. Mass divided by volume will give you the density of the material of this product, of this block. Clear? That's about the cubic block. Same way PVC tube. PVC tube, now look at this. This is how the tube is going to be. This is how the tube is going to be. So you take the internal diameter, external diameter. Look at this. Right. So internal diameter, external diameter, let's mark it. Right. See, internal diameter, let it be D1. External diameter, let it be D2. So this cross-sectional area, that means this area, see this colored area, the cross-sectional area of that will be pi D2 is the external diameter. D2 by 2 is the radius squared minus pi D1 by 2 squared. Pi D1 by 2 squared. That will be the cross-sectional area. And then if you know the length of this tube, then the volume will be, cross-sectional area is going to be pi D2 by 2 squared minus pi D1 by 2 squared. This is the cross-sectional area multiplied by length, That's what the volume of material used in this PVC tube. For that also, if you measure D1 and D2, L also you have to measure. Right? If it is less than say 10-15 centimeters, you can use the vernier caliper itself and measure the length. If not, you can use the meter ruler or meter stick and measure the length. Right, depending on how long it is, less than 15 centimeter, you can go for the vernier caliper itself because that's more accurate. But it's more than 15 centimeter, vernier caliper won't be enough to measure it. Then you have to go for a meter ruler, find the length and find the volume of it like this. Mass you can find using the tri-beam balance. Mass divided by volume will be the density. So most of the questions are connected to the density, but what we find using these measuring instruments is volume. This is also like when you get the diameter, see, you first get the diameter in this direction, then what you do, we have to get the diameter in this direction as well. So what you do, you rotate it and get perpendicular. 90 degrees you rotate it and get a perpendicular direction diameter as well. Average of that will be the diameter at this point. Then if you have the tube like this, see, if you have the tube like this, if this is the tube, you get the diameter at this point, another point. 3 different points you take the diameter. That also, each point you take 2 measurements, one direction, perpendicular direction. Right, so at this point you take 2 measurements like this, get the average, and move the tube a little bit in or out, move on to another point. Again there take 2 perpendicular directions and get the average of it here. So at 3 different points you get diameters and then get the average of all those 3. That will be taken as the diameter of this PVC tube. Why is that? Again the same argument, the diameter, even though it looks like a uniform tube, there might be slight variations. So to average out all those fluctuations, we take the diameter at multiple points and average it. That's about PVC tube. Solid sphere is easy. That's how the sphere is going to be. So you know 4 by 3 pi r cube is the volume. Right? So you need to get the diameter, keep it like this and then rotate it, keep it like this. And again you can rotate in two planes. You can rotate it like this as well as you can rotate in the other direction. So actually you can get 3 perpendicular diameters. 3 at one for the same sphere, you can get 3 perpendicular diameters. Look at this. If you get one in this direction, another one can be taken in this direction, another one can be taken in this direction. Because you can rotate it in 2 planes. If you take a tube, it can be rotated only in one plane. Here you can rotate it like this as well as the other side. So rotate it differently and get different measurements for 3 diameters and then get the average. Then the volume will be 4 by 3 pi d by 2 cube. Remember, what we measure is diameter. I repeatedly say that because they ask what measurement you take, still half of the students write radius. You never measure radius, you measure diameter. Get the measurement for diameter, divide by 2, that's going to be the radius. Right? We can't measure the radius, we can measure only the diameter. That's solid sphere. And then hollow cylinder, look at this. If I take the external diameter as D1, internal diameter as D2, then external height as H or H1, and internal depth is there because there can be a thickness of this bottom, so depth is different, depth can be H2. So imagine, how do we find the volume of this? If this hollowness is not there, if it is completely a solid cylinder, then pi external diameter is D1. So D1 by 2 squared into height H1. This would have been the volume if the middle part is not taken out. That means if it is completely a filled cylinder. But now from the full cylinder, another cylinder has been taken out. What part of cylinder has been carved out here? Carved out means taken out here. The middle cylinder, like what is missing in the middle, which has a diameter of D2. So pi D2 by 2 squared, D2 by 2 squared into H2, Clear? This would be the volume of it. So what measurements we have to take? D1, external diameter. You can use the external jaws. Internal diameter, internal jaws. Height, if it is less than 15 centimeter, you can use the vernier itself. External jaws will be enough for that. External jaws. Depth. Did you see in the vernier caliper there was one part, see, a small needle-like thing, we call it depth probe. That's a like needle-like thing which can be extended and you can insert it into the cylinder. And get the reading. We can use that. So to measure the depth, you can use the depth probe. Right? That's how you measure the readings. You have to get 4 readings here: internal diameter, external diameter, height of the cylinder, and the internal depth of the cylinder. Right? With all those 4, you can get the volume of this hollow cylinder. Right? That also, like each measurement you have to get at multiple places. When you say internal depth, you don't measure at one point. You measure at multiple points, get the average. Height, you don't measure at one point. Measure because the same reason. The height may not be uniform. The height may not be equal at every point, every place you measure. Right? We need to average out. If there is any fluctuation, we have to get the average of it. Because of that, we get multiple readings at multiple places and get the average. Clear? Right. So that's how we are going to use the vernier caliper. Now let's take a real vernier caliper, get these readings and show it to you how we do it. Right? The apparatus that we are going to use in this experiment, this is what we call vernier caliper. Right? This is what we call vernier caliper. I'll show you, I'll explain how we are going to use this. Look at this, vernier caliper. And this is a glass block, a rectangular glass block. Sometimes we use wooden block. So how do we find the volume of it? You have to find the thickness, you have to find the length and width. All 3, how precisely we measure using a vernier caliper, I'll show you now. This is the test tube. You can measure the external diameter and internal diameter of this test tube. Then you can find the thickness. If you get the difference between external diameter and internal diameter, that will give you twice the thickness. Because when you say twice, see, we are going to measure the external diameter, then we will measure the internal diameter. So when you subtract, twice the thickness will be captured, twice the thickness. Right. So from that you can find the thickness of this test tube as well. This is a metallic sphere, spherical shaped metal, a metal ball actually, we can find the diameter of this. How to find the diameter of a sphere shaped one using vernier caliper we can see. This is a cylindrical shaped container, right, a hollow cylinder. We can find the depth of this. The depth of this you can't find using a meter ruler because you won't be able to send the meter ruler inside this. Right. So, this hollow cylindrical shaped container, how do, since it is very small, how do we find the depth of it? Because if you find the depth and then the internal diameter, then you can find the internal volume of it, right, the capacity of it. So, how we are going to find that? All that I will show with this vernier caliper. Before we start using this vernier caliper, I have a sample of this vernier caliper to show it to you to understand the principles of vernier caliper. Because this is too small, the enlarged version of this. Because if you see vernier caliper, the vernier is only this much. So, length of the vernier is not even a centimeter. Right, even though the full length is 15 centimeters, 16 centimeters, the vernier's length is only 1 centimeter, 10 millimeters. So, you may not be able to understand everything with that small scale, you may not be able to observe everything. So, we have a enlarged version of this as a sample for you to understand the basic principles of vernier caliper. So, now I will show you that sample, and with that sample I will explain you all the principles of vernier caliper. After understanding the vernier caliper, then we will come to vernier caliper and find all the measurements. Students, you can see, now this is the sample I told you, it is a sample of a vernier caliper. You can see there are two scales. One is a lengthy continuous one and there is a short one. The lengthy one is what we call main scale. This is what we call main scale. This is what we call vernier scale. The short one, the small one is what we call vernier scale. On the main scale, vernier scale can be moved. See, it's movable. It's movable. It's movable like this. Right. There are three basic things that you need to understand on a vernier caliper. One is called least count. Least count means the minimum measurement you can take from a vernier caliper. Second one, zero error. Third one, how to get the reading. Least count, zero error, how to get the reading. All those three we are going to see on this sample. Then we will take the actual vernier caliper and get the readings. Right. Now, see, I am moving this vernier caliper and bringing the zero of the vernier scale and main scale together. Can you see? The zeros are aligned. Both zeros I have aligned. Look at the main scale. What we mark as 10 in main scale is actually 1 centimeter. This is 1 centimeter. So, 1 centimeter is divided into 10 subsections, where each subsection is 1 millimeter, because 1 centimeter divided by 10 is 0.1 centimeters. That is what you call a millimeter. So, like the meter ruler, like the foot ruler that you use, 1 centimeter is divided into 10. So, it's just the meter ruler scaling that you have on the main scale. Right, this is 1 centimeter and each of this is a millimeter. Right. Now, look at the vernier scale. Vernier scale also has 10 subsections, but each of them is not 1 millimeter. How do we find the width of it? Look at this. Vernier scale's 10th segment exactly aligns with the 9th segment of the vernier of the main scale. Repeat, vernier's 10th scale aligns with 9th scale of the main scale. Look, 5, 6, 7, 8, 9. So, actually from here to here it is only 9 millimeters. That means vernier scale's 10 sections are equal to 9 millimeters. 10 sections, 9 millimeter. So, one section must be 9 by 10, which is 0.9, 0.9 millimeters. So, each of these sections from here to here is 0.9, another 0.9, another 0.9. That is how the vernier scale comes. Understand, this vernier scale has it like this. Some other vernier calipers might have different number of scales in vernier, different number of sections. Some have 20 sections that will match with 19 sections of the main scale. Then the calculations will be different. Here I am explaining you, vernier has 10 scales and those 10 scales are equal to 9 scales of the main one. Understood? Right. So, what is the meaning of least count? Now, look at this, come to this point, 0 to 1. This is 1 millimeter, right? On the main scale, one section means 1 millimeter. On the vernier scale, one section means 0.9 millimeter. Look at this, from here to here, up to here, it is 1 millimeter. From here to here, it is only 0.9 millimeter. So, between these two lines, there has to be a difference, right? That means, first scale of the main scale and the first section, first mark of the vernier scale, they are not together, they are not aligned. There is a small gap. How much is that gap? This is 1 millimeter, this is 0.9 millimeter. The difference has to be 1 minus 0.9, 0.1 millimeter. The difference, the gap between this and this. That is what we call the least count. Least count. That means, that is the minimum measurement, that is the least measurement we can take from this vernier scale, this vernier caliper. So, how the least count is defined is, one subsection of main scale's length minus one subsection of vernier scale's length. 1 millimeter, 0.9 millimeter, the difference is 0.1 millimeter. So, whatever the measurements we get using this vernier caliper has to be in multiples of 0.1 millimeter, not anything less than that. You can't get 0.05, you can't get 0.08, second decimal is not possible, second decimal of a millimeter is not possible with this vernier scale. The least value you can measure from this is first decimal, that is 0.1 millimeters, right? That is what we call least count. Second point is zero error. Zero error means, now I told you the vernier scale is freely movable like this, but there is a limit. There is a limit. When you come and like align to the 0, I will show you in the vernier caliper. Look at this. Look at this. See, this is the vernier scale. This is the vernier scale, this one. That is what movable. Can you see it moves? And this is the main scale, like I mentioned here. So, when I close it, look at it, when I bring these two closer, at some point they get closed. That means there is no, look at this, right. When I close it, see this gap becomes lower and lower, less gap. At some point that gap becomes 0. So, that is where the vernier and the main scale are closed. There is no gap in between them. In that situation, look at this. In that situation, if there is no error in the vernier caliper, then as I mentioned earlier, both zeros have to be collinear, they have to be aligned. A perfect vernier scale, vernier caliper will be like that. But sometimes they may not be aligned like this. They might take a position like this, where both zeros are not aligned towards one side, or it can take to the other side. See, based on this we call it error, positive error and negative error. Positive error means once the caliper is closed, the vernier 0 is not aligned with this 0. Also, it's on the positive direction. Now, on this direction only scale is increasing, right? On the positive direction, vernier 0 is there. From the 0 of main scale, vernier 0 is on the positive direction. This is the positive direction. See, from here to here. That's what we call positive error. If it is on the other direction, say if it is here, from this 0, vernier 0 is on the negative direction, the other side. Then you call it negative error. So, see, think about a weighing scale, an electronic weighing scale. Ideally, it has to be 0 when there is nothing placed on a weighing scale. Say you keep something, if it shows 50 gram, 0 to 50 gram, reading is 50 gram. But imagine there was an error on the weighing scale. So, when you switch on the weighing scale, it is already at 5 grams. It shows you 5 grams. After it shows 5 gram, then you keep something on it. Now, the measurement you get is 50 gram. So, what is the weight of the item that you have kept on the weighing scale? It's not 50 because it was at 5 originally. From 5 gram, it has come to 50 gram. Then it has to be 45 gram, right? So, from the reading of 50 gram, you subtracted that error 5 grams to get the actual value. Similarly, imagine if the weighing scale can show some minus values also. Let's say it has shown minus 4 at the beginning. Originally, it was minus 4 initially. Then you kept some goods on it. Now, it shows 50 grams. What's the actual weight of that good? It's not 50 because from minus 4 it has to come to 0 and then it has to go to 50. So, altogether it's 54 grams, right. So, depending on the error, sometimes we have to subtract the value of the error, sometimes we have to add the value of the error. I will show you how. We will consider a positive error scenario. Look at a situation like this. It's a positive error. Right. Imagine this is this you can see this is the error. Main scale 0 is here, vernier scale is here. So, this is the error. How do we find this error? What's the value of it? Because it's not even 1 millimeter, because 1 millimeter means here. The error is less than 1 millimeter. It's less than 1 millimeter. How do we find that? I'll tell you the easy way. Look at this. On the vernier scale, see which line coincides with the main scale. Is it coinciding with the main scale? No. Is it coinciding? No. 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 Look at this one. These two coincide, right? One line of the main scale, one line of the vernier scale, they coincide. Right. Consider this. Let me keep the pencil there. Look at the main scale now. From here to here 1 millimeter, 2 millimeters, 3 millimeters, 4 millimeters. From 0 of main scale to this line, it's 4 millimeters. Look at the vernier scale, 1, 2, 3, 4. So, from the 0 of vernier, 4 sections, you know one section is 0.9 millimeters, 4 into 0.9, 3.6 millimeters. From here to here, it's 3.6. So, look at this. On the main scale, this much is 4 millimeter. On the vernier scale, this much is 3.6 millimeter. The difference has to be the error here, right? 4 millimeter, 3.6 millimeter, 0.4 millimeter is the error that you get here. Understand? So, you need to find out where these two lines are becoming collinear. They must be aligned. From that only you measure the main scale distance, vernier scale distance, difference is the error. But there is a shortcut to find that. How do we find the shortcut? On the vernier scale, this is the first one, second one, third one, fourth one. Fourth section of the vernier scale is aligned. That means 4 into least count 0.1 millimeter, 4 into 0.1, 0.4 millimeter has to be the difference. Right? When 4 sections of vernier scale is aligned here, You know, each section will have 0.1 millimeter difference, right? See, here you will have 0.1. Here you will have another 0.1, so it becomes 0.2. Here you have another 0.1, so it becomes 0.3. With this, another 0.1, it's 0.4 millimeters difference. So here the value of error is 0.4 millimeters. And the formula is this. Once you get the reading, reading minus error has to be the answer. The actual value, actual length that you measure, whatever the reading you get minus 0 error. So if I get a reading of 30 millimeter here, 30 minus 0.4 millimeter would give me the actual length that I have measured. And this is a positive error. So error will come with a positive sign itself. So reading minus positive 0.4. Minus is there in the equation, reading minus positive 0.4. So if you measure 30 millimeter, 30 minus 0.4. 29.6 has to be the value of it. Similarly, let me show you negative error, minus error. Right, look at this situation. Can you see, this is where the main scale 0 is. Vernier scale has gone to the negative side. Passing the 0, it has gone. This is what we call negative error. How do you find that error? Let's first find it conceptually. See, the third line of the vernier, 1, 2, 3. This line is where lines are aligned. Can you see, this is not aligned, this is not aligned, this is aligned. All others are not aligned. So here I keep the pencil. Now look at the vernier scale, 1, 2, 3. 3 subsections. 3, you know, each is 0.9 millimeter. So from this 0 to this pencil, 3 into 0.9, 2.7 millimeters. Look at this main scale, 1, 2. There are 2 sections, 2 millimeters. This 0 to pencil, that means vernier 0 to this third scale, 2.7 millimeters. Main scale 0 to this line, 2 millimeters. So the gap here has to be 2.7 to 0.7 millimeter has to be the difference. So this is called minus negative error. So I'll put the value as the value of error is minus 0.7 millimeters. For that also there is a shortcut. What is the shortcut? You know, third line of the vernier is aligned, 1, 2, 3. Altogether there are 10 lines, 10 sections. So 10 minus 3, because the minus error, from n total number of scales in the vernier, you subtract the number of scales, which line that coincides, third line coincides. Altogether 10 lines are there, 10 minus 3, 7 lines. Least count is 0.1, 10 into 0.1, 10 minus 3, 7, 7 into 0.1, 0.7 millimeter. Either you can take conceptually, like getting this length subtracted, or else do like this, altogether 10, 3 coincides, it's a minus error, so 10 minus 3 is 7 into 0.1, 0.7 millimeter. Negative error, so we put it as minus 0.7 millimeter. So when there is minus error, negative error, suppose you get a reading of 30 millimeter, you are going to put it as 30 minus error, right? Reading minus error. 30 minus error is going to be minus 0.7. So it becomes 30 minus 0.7. Minus becomes plus, 30 plus 0.7. So the final value will be 30.7. So this is why I told you, if it is a positive error, value of error is subtracted from the reading. If it is a negative error, the magnitude of the error is being added with the reading. Be familiar with this. Easy example for you to remember, that weighing scale, if it is at 5 grams, goes up to 50 grams, 45 is the increment. If it is at minus 5 grams, if it goes up to 50, 55 is the increment. Understand that. So that's the second thing that you need to understand on a vernier caliper, positive 0 error and negative 0 error. Once you have checked your vernier caliper about this 0 error also, first thing you do, finding the least count. Second thing you do, finding the 0 error. Third thing, you can get the readings. The readings, I'll show you one example of reading here. Let's say, okay, this is how the reading is. When you are measuring some length, this is how the vernier shows you. So how do we get the reading? Simple, look at this. Look at the vernier scale. Look at the vernier scale. First check where the 0 is, this is where 0 is. So vernier scale 0, so which means this is the total length that we are measuring now. From this 0 to this 0, that's the length we are measuring. First count the main scale sections. How many sections of main scale? Up to here it's 10, 11, 12. 12 sections are complete. 13 is not yet complete. 12 point something, 12 millimeter plus this much. Plus this much. Up to here it's 12 millimeter. See, here it is 12. Why do I take this section? Because vernier 0 is here. So right before the vernier 0, how many full sections are complete in the main scale? 12 full sections are complete. Then I have to get this difference. How do I get that? Check which scale coincides. 1, 2, 3. See, this one coincides. Others don't coincide. This doesn't coincide. This doesn't coincide. This doesn't coincide. See, this is only one. Only one section will coincide. If there are two sections coinciding, then something is wrong with the vernier caliper, or else something is wrong with your eyes. Right? There can't be two sections coinciding with the main scale. Only one will coincide. Right? So this is the one coinciding. 1, 2, 3. Third one coincides. Least count how much for this vernier caliper? 0.1. 3 into 0.1, 0.3. This difference is going to be 0.3. So up to here it's 12, 12.3. 12.3. The reading that you get now is 12.3 millimeters. Let's take another example. Look at this case. How much is the reading? 0 is here, 10, 11, 12, 13, 14. 14 millimeters complete. Then how much will be this difference? 1, 2, 3, 4, 5. Fifth section of vernier coincides. Fifth section coincides means that's 5 into least count, 0.1, 0.5. So 14.5 millimeter it has to be. This is how you get the readings. How did this become 0.5? You can think from here to here, it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 main sections, 5 millimeter. 1, 2, 3, 4, 5. 5 vernier sections, 5 into 0.9, 4.5 millimeter. This is 5 millimeter, this is 4.5 millimeter, difference will be 0.5 millimeter. But easy option for you, count the number of sections that coincides. 1, 2, 3, 4, 5. 5 sections coincide of the vernier caliper, vernier scale. 5 into least count 0.1, that will be 0.5. So main scale up to here it's 14, this gap has to be 0.5, 14.5 millimeter. That's how you get the reading. After getting the reading, if there had been a 0 error, adjust for the 0 error, you get the correct value of the length that you measured. Understand? So now do you understand what is meant by least count of a vernier caliper? How to find that? It's not always 0.1. Here we had 10 scales coinciding with 9 scales here. Based on that, it became 0.1. Different vernier calipers will have different least counts. You must be able to calculate that. Least count, 0 error, and then how to get the reading. Okay. So this is what the basics of vernier caliper is. Now, with this much of understanding, we'll take our vernier caliper and start measuring all those that we wanted to measure. Right, students. So let me take the vernier caliper. The least count is same as what I explained because there are 10 lines in the vernier caliper, vernier scale, and those 10 are aligned with the 9 scales of the main one. Therefore, the least count is 0.1 millimeter itself. Let me check whether there is 0 error. See, when these two are closed, when both calipers are closed, the 0 of vernier and the 0 of main scale are aligned together in the same line, which means there is no 0 error. There is no 0 error, right? So I can get the readings, and the readings will be equal to the actual length that I have measured. First thing I am going to measure. So now the first thing, let me take this glass block. Sometimes we use glass block, sometimes we use wooden blocks. This is a rectangular glass block. Imagine if I want to find the volume of this, I need to find the thickness, I need to find the width, and I need to find the length, right. So, let us say now I want to measure the thickness of it. How do we measure the thickness? In the vernier caliper there is this screw. You roll this screw and you can increase the gap here. See, can you see these calipers, they move relatively. After increasing the gap there, we will keep, after increasing the gap there, we will keep this glass block like this and let us close it. Again, use the screw, keep pushing. Do not push the vernier caliper with your bare hands. You have to close it using this screw, right. When you roll it, it keeps moving. At one point it gets locked. After it gets locked, even though the screw sounds, it's rolling, the vernier will not be moving. The vernier scale will not be moving. That means it's locked. Once it is locked, look at this, you have a screw here, right, actually a bolt and a nut. If you tighten this nut, then what happens at this position, the vernier scale gets fixed. Then even if you take this block out, it does not move, right. So, let me check again, let me loosen this, close it, right. Now, I want to find the thickness. Let me take the measurement. What do I have to check? I told you how to get the measurement. We need to see where the 0 of vernier is in between, like what is the last section of main scale before the 0 of main scale. That is what I have to check. We can check like this with the bare eyes. If it is not so clear to you, you have another option. You can use a magnifying lens like this, right. If it is not very clear to you, usually you should be able to observe, you can get the readings with the bare eyes, but if you want to magnify and see, you can use the magnifying lens also. I can see the main scale is at 2.4, that means 2.4 centimeters, which means 24 millimeters. That means 0 of vernier is right after 24th section of the main scale. Let me double check. Yes, it has passed 24. It has passed 24, but it has not passed 25. In between 24 and 25, 0 of vernier scale is there. Now, I need to check which scale of vernier aligns with another one in the main scale, right. Sixth scale of the vernier is aligned with another line on the main scale. So, when you say 6 scales, the least count is 0.1, 6 into 0.1, 0.6 millimeters, 0.6 millimeters. So, already on the main scale we had 24, now in the vernier scale we get 0.6. So, the total reading we get here is 24.6 millimeter. The 6th scale of the vernier is aligned with another line on the main scale. 6 scales means the least count is 0.1, 6 scales into 0.1, it is 0.6 millimeters. Already on the main scale we had 24, now 0.6 on the vernier scale. So, altogether 24.6 millimeter is the reading I am getting, and there was no 0 error as well. So, 24.6 is the actual thickness we are getting, right, 24.6 millimeter. There is one thing we need to understand. If you want to get the precise reading for thickness, you do not measure at only one place, you measure the thickness at multiple places and you can get the average, because the thickness might slightly vary place to place, point to point. So, let me check the thickness at another point again. Let me check at this point. Let us close it. With the bare eyes itself, I can see 24 millimeter passed. That means in the main scale 24 has been passed, but it has not passed the 25. That means it has to be in between 24 and 25. Now I need to check the vernier scale. In the vernier scale, 9th section coincides with another line in the main scale. 9th section means 0.9 millimeters, isn't it? Least count is 0.1. So 24 on the main scale, 0.9 on the vernier scale, altogether you get 24.9 millimeter thickness in the second reading. So already we got 24.6 millimeter, now we got 24.9 millimeter. I can get the mean value of these two. That would give me a proper accurate thickness of this glass block. Similarly, I can actually measure the width, I can measure the length, and I can find the volume of this. Same way I have measured the thickness, you can measure the width as well. Width, you can measure the length, and you can find the volume of this block. It can be a glass block, it can be a wooden block, whatever the type of rectangular block you have. This method, you can use the vernier caliper to find their dimensions and find the volume. So this is one use of vernier caliper. The other use you have about the vernier caliper, let me take this sphere, right? It's a metallic sphere. If I want to find the volume of this, since it is a uniform sphere, I just have to find the diameter of this, radius. But if you find the diameter, half of diameter is radius, right? So how do we find the radius or diameter of this? See, let me take the vernier caliper, increase the gap here, keep it in the middle, right? Let's say, okay, I'm going to measure like this. Keep it in the middle, right? Make sure it's right in the middle and close these calipers. See? So after you have closed the calipers at the right point, now what you can do, you can tighten this screw so that the vernier doesn't move. Let me double check. Did I keep it at the right point? Yes, it's at the right point. Understand? Now you don't have to keep this sphere in the middle. You can even take it out and get the reading because I have tightened the vernier, so the vernier scale will not move now, right? Now let me check the reading. The 0 of vernier has passed 24 of the main scale, 24 of the main scale. Now I need to check which line of vernier aligns with another line on the main scale. Maybe I can use this magnifying glass so that I can get a better view, better observation. The 7th section, 7th line of vernier scale is aligned with another line on the main scale. That means it has to be 0.7 millimeters. So 24 on the main scale, 0.7 on the vernier scale, 24.7 millimeter is the diameter I am getting. Like what we did for the thickness, diameter also we will not measure at one point. See, this is where we got 24.7. Now perpendicular to that at another point, let me again get the thickness, diameter. Not only twice, you can get it at 3 or 4 different points, get the diameter, and you can get the average also. So now I am trying to get it at 2 different points. So I am getting at a different angle, but make sure it's right at the middle of the sphere. This time also it has passed 24 on the main scale. To check the vernier scale, the sixth line of vernier scale aligns with another line on the main scale. Sixth line means 0.6 millimeters. So, 24 on the main scale, 0.6 on the vernier scale, 24.6 millimeters is the reading you are getting this time. So, 24.7 was the first reading, 24.6 is the second reading, get the average between these two, that will give you an average diameter of this sphere. How to use these calipers, find the thickness, find the diameter, I have shown you now. Now, let us take this test tube, right. Test tube, I need to get the external diameter because I am going to find the thickness. I am going to find the thickness. So, to find the thickness, this is the plan. I am going to find the external diameter, I am going to find the internal diameter, difference has to be twice the thickness. When you say diameter, the thickness is captured twice. So, difference in diameter has to be twice the thickness, right. So, see how we get the external diameter and internal diameter. External diameter as usual, keep it here, close it and get the reading, right. So, after closing it, make sure you tighten the screw, you have tightened it, you can take the test tube outside and you can get the reading. The main scale I can just check it, the 0 of vernier is right after 24 of the main scales. So, this is also at 24 millimeter plus something. I need to check the point where it coincides with the vernier scale. Third scale of the vernier, third line of the vernier coincides, that means 0.3 millimeters from vernier scale you get, 24 on the main scale, 24.3 millimeter we get the external diameter of this test tube. It is as same as getting the thickness of the glass block, the sphere's external radius, similarly we have got it 24.3 millimeter. Now, the new thing I am going to show you how to get the internal diameter. See, internal diameter. To get the internal diameter, look at this. See, you have another two calipers here. Can you see? Right. That is what we have now. This is what we use to measure the external diameters, external widthness and all. External width and all. To measure the internal diameter, internal width, anything, you can use the caliper on the other side. See, when I close it, those two will be aligned. Can you see? When I open it, they move in the opposite direction. See, it moves like this. So, look at this. Let me keep this caliper inside, inside, and start widening the gap. At some point, it touches the both walls of this, both side walls of the test tube and it gets locked. It gets locked. Now, still when you rotate the screw, screw is rotating, but the caliper is not moving. That means, at this point if you get the reading, that should give you the internal diameter. Right. So, can you see the caliper that I am using to find the internal diameter? The small calipers, right. At this point, let me get the reading. First, let me check where the 0 is. 0 of vernier scale is right after 22 of the main scale, right after 22 of the main scale, right, 22, that means 22 millimeter plus. And then where the vernier scale coincides is one, two, three, four, 5. The fifth line of vernier scale, coincides. That means it has to be 0.5 millimeter, 22 on the main scale, 22.5 millimeter is the internal diameter of this, right. So, we already got the external diameter as 24.3, internal diameter as 22.5, you get the difference, you can get twice the thickness of this test tube. Understand? So, this is what we use for internal diameter. Clear? How much we got for this test tube? We got 22.5. So now you have understood how to use these external jaws and internal jaws, right? To measure the external diameter and all, we use this external jaw, and this is the internal jaw that you use to measure the internal diameters. And imagine a cylindrical container like this. If I want to measure the depth of this, I can't use this jaws for that. For that, what we have, can you see the pin here? There is a pin on the other end of the vernier caliper, this pin. I'll be using this pin to measure the depth, right? Look at this. You keep the pin like this so that it goes and touches the bottom. Then what do we do? You roll this and bring this closer. Look at this again. Look at this again. You keep it like this and roll the screw and bring it. So you can see when this comes down, the gap here up to the brim of this container, you can bring it down. Right. Can you see? Now it's closed. The main scale touches the brim of it, and the pin touches the bottom of it. Right. Look at this carefully. Now this is an instance where the brim touches the main scale and the pin touches the bottom of it. At this point, if I get the reading, that will give me the thickness, that is basically this much. That will give me the depth of it, this much. This much can be measured. So that's why we have this third kind of arrangement, a pin kind of arrangement here to measure the depth, right? So let's see what's the reading we are getting now. The zero of vernier just past 5 centimeter mark. 5 centimeter mark means that is 50 millimeter mark. The zero of the vernier has just passed the 5 centimeter mark. 5 centimeter means it's 50 millimeter mark. And then I have to find which line of vernier coincides with the main scale. The third line of vernier coincides with the main scale, right? The third line. So that's 0.3 millimeter, 50 on the main scale, 0.3 on the vernier scale, 50.3 millimeters is the depth of this, right? Then I can use this internal jaw and find the internal diameter. If you know the internal diameter, if you know the internal depth of it, then you can find the internal volume, that's basically the capacity of it. The depth also you can measure at different points and you can get the average. Similarly here the thickness also I measured at one point. See, I measured like this. You can again measure perpendicular to that, get the reading, get the average. So always, getting the readings from multiple points and getting the average would give you more accurate answers. Understand? So now are you clear about the basic concepts of a vernier caliper? Remember the 3 points I told you. One is about least count, how to calculate the least count. Second, how to find the zero error and identify whether it is a positive zero error or negative zero error. Third one, how to adjust for the zero error also. Third one, getting the readings. I explained all that with a sample of a vernier caliper. Then using the vernier caliper, external jaws, internal jaws and the pin, how to get the readings. See, external jaws, internal jaws and the pin, how to get the readings. External diameter, external width, all that with the external jaws. Internal diameter with the internal jaws. Depth of something with the pin. Right? I have shown you example for each of them, how to get the readings. Right? So go through this, you will be able to answer all the questions that you get in the exam regarding a vernier caliper. The next experiment we will be doing in physics, we will see another measuring equipment. I'll show you another measuring equipment, and we'll try to understand the basic concepts and the way to use another measuring equipment. All right, students. Now, let's see some past paper questions that have come from this particular experiment. That means using vernier caliper or related to that, if there are past paper questions, let's see them one by one. So, I have taken a very old past paper, 1984. The diagram shows a vernier caliper that has been calibrated to measure the diameter of a metal cylinder. The vernier has been magnified. Okay. Diameter of metal cylinder, vernier has been magnified. Alright, okay. We'll come to this later. If 10 divisions of the vernier coincides with 9 millimeter of main division, what's the measurement of cylinder's diameter? Let's get the least count first. Let's say one vernier is going to be 9 by 10 millimeter, which is 0.9. So, least count is going to be 1 millimeter minus 0.9 millimeter, 0.1 millimeter. That's least count, but they are asking what's the measurement of cylinder's diameter. So, diameter, now look at this, 21. After 21 millimeter, vernier 0 comes. So, it has to be 21 plus in millimeters. See which scale coincides or aligns with main scale. Here, this one. That is 1, 2, 3, 4, 5, 6th division. Vernier's 6th division is aligned with main scale division. So, 6 into least count. 6 into least count. You get 21.6 millimeter, careful, millimeter. In centimeters, if you want to say 2.16 centimeter, 2.16 centimeter. 50 vernier divisions of another more accurate measuring instrument coincides with 99 half millimeter divisions of main scale. What's the least count? I explained this when I explained the theory. So, 50 vernier is 99 half millimeter scales. So, 1 vernier 99 into 0.5 over 50, which is 0.99. Now, understand, the main scale is going to be like this. This is main. Whereas vernier is going to be like this. 1. This is vernier. So, this is what the least count is. That means 2 main scale division minus 1 vernier division. 2 main scale division minus 1 division. 2 main scale 0.5 millimeter minus 0.99 is the vernier division. So, this is 1 millimeter, 0.99, 0.01 millimeters, 0.01 millimeters. After taking the measurement for cylinder's diameter, when the jaws were fully closed, the 0 of the vernier scale did not coincide with the 0 of the main scale as shown in the diagram. The instrument is considered to have 0 error. What is the value of the 0 error? What is the corrected value of the cylinder's diameter? 0 error, can you see which one is coinciding here? This one. 1, 2, 3, 4, and it's on the positive side. So, I can say 0 error is 4th division, 0.4 into 0.1 millimeter. Isn't it 0.1 millimeter or 0.01 millimeter? 0.99 millimeter. This is 5 or 100, yes. 0.01 millimeter. This is the main one on the main division, right? So, this is not 49 and 100. So, 0.1 is correct. Let me write it again. 4th division into 0.1 millimeter, 0.4 millimeter. 4th division, this is 4th division, and this is the first diagram, not this one. This is about the previous one. Here, least count 0.1, this one 0.4. So, the corrected value of diameter, what was the reading we got? What was the reading? 21.6. 21.6. And you have a positive zero error of 0.5. Subtract it. 21.2 millimeter. 21.2 millimeter. 21.2 millimeter. Next. In some vernier calipers, error arises as zero of the vernier scale remains behind the zero of the main scale as shown in the diagram. Find the zero error of this vernier caliper. So find the zero error, see like where it matches. This must be the line. This is the line that becomes collinear. So like going from basics, now this is the error. So you get 1, 2, 3, 4, 5. 5 vernier scales minus 4 main scales. This much minus this much will give you the error. 5 into vernier scales 0.9, we found it earlier. 4 into 1. 4.5 minus 4.5 millimeter. Negative error. By negative error, 0 is on the other side. Vernier 0 has gone to the other side. Right. To find this, I can give you another method. Look at this. Not the 5th division. No, it has to be the 3rd division here. Here, 3rd division seems to be collinear correctly. Third division. See, this is the one seems to be collinear. Then I have to say third division. So then 3 vernier scales minus 2 main scales. 3 into 0.9 minus 2 into 1. 2.7, 0.7. 0.7 millimeter. Another method to get this like this. Look at this. Vernier has altogether 10 scales. Out of 10 scales, third one is the one being aligned. Third one. So subtract that and multiply by the least count. If it is positive error, what do we do? Whichever the division that aligns, multiply by least count. If third division is there, 3 into 0.1. But if it is negative error, from the total divisions of vernier scale, subtract the one that is being coincided and get the balance, multiply by least count. So 7 into 0.1, 0.7 millimeter. 0.7 millimeter. Clear? But negative error it has to be. What is the function of screw C in the vernier caliper? Where is screw C? Let's go and see. Screw C is here. Screw C. So what's the function of screw C here? Using that only we are going to move the jaw, right? And that will show us when it gets in contact with the object that we are going to measure, C will show us, right? It will not, after that even when you rotate it, the caliper will not move. Caliper will not move. So let's say C is to move the jaws in and out. What is the function of the pair of jaws D? Which is pair of jaws D? This one. Internal jaws. This is used to measure the internal diameter of hollow cylinders, tubes, etc. To measure internal diameters. A particular string's diameter is 0.18 millimeter as per the manufacturer's book. This value cannot be verified using the vernier caliper in the main diagram. Give reasons for this. We can't verify this because 0.1 millimeter is the least count of the vernier in the main diagram. So 0.1, 0.2, 0.3, 0.4, that's how you can get the measurements. 0.18 millimeter you cannot measure. You cannot measure 0.18 millimeter. Right. So let's write it. since the least count is 0.1 millimeter, 0.18 millimeter cannot be measured, can't be measured. If you have space, you can write only multiples of 0.1 millimeter can be measured. Or you can say measurements can be only in multiples of 0.1 millimeter, multiples of least count, not any part of it. 0.08 millimeter, that is not possible. You can measure 0.1, you can measure 0.2, nothing in between. Alright, that's all from that question. Very simple, very straightforward. Now let's move on to another question, 1995. The diagram shows a thin metal square plate of side A, okay, side length A, with a square hole of side B. Okay. A and B are in few centimeters. A, B, thickness T and mass M of this plate have been measured as accurate as possible. What is the most suitable instrument in laboratory to measure thickness? To measure the thickness, vernier caliper won't be enough. You need more accurate instrument because vernier caliper goes up to 0.1 millimeter. But since this is a very thin plate, something like a blade, you won't be able to measure the thickness of it. We have to use the next instrument that we have to see in the experiments. We haven't seen that yet. In the second experiment, I will show you micrometer screw gauge. Micrometer screw gauge is more appropriate to measure the thickness of plates which are very small, like blade. Micrometer screw gauge. Micrometer screw gauge. A check has to be done before taking measurements using the above instrument. What is that? That means the zero error. A check means zero error. Zero error means, like here we have vernier scale and main scale in vernier caliper. There you have a circular scale, which is the vernier. Circular scale and the main scale. So circular scale 0 and main scale 0 must be aligned, must become collinear when we start doing the experiment. Then only there is no zero error. If there is zero error, we have to check that, right? To check whether the zero of circular scale aligns with the zero of main scale. Next, you are given a vernier caliper to measure A and B. Which parts of the vernier caliper will you use to get the measurements? A is the external width. For that you can use the external jaws of vernier caliper. B is the width of the hole in the middle. For that you are use the internal jaws. A, external jaws. B, internal jaws. Internal jaws. What is the most suitable laboratory instrument to measure M? Measure M, if you think it's of very lightweight, if it is less than 1 gram or close to that, we can go for the chemical scale. Chemical scale. Right. Write a formula for the density of this metal using M, A, B and T. Density has to be mass divided by volume. Mass divided by volume will be, look at this. This is A. So A squared is the full cross-sectional area. From that B squared has to be subtracted. A squared minus B squared into thickness. A squared minus B squared into thickness. Clear? Values for T taken at 5 different points are given below. What is the least count of the instrument used? You know, The readings have to be in multiples of the least count. So here, check the second decimal. Okay, this is 10 millimeter, 0.10, 0.11, 0.12, 0.12, 0.11. So it has to be 0.01 millimeter, correct? If it is 0.02 millimeter, you can't measure this one. 1.11 will not come as a multiple of 0.02. 0.05 not possible, right? 0.01 is the only possibility that can give you all these. 0.01 millimeter. Find the average thickness of the plate. Average thickness of the plate. When you say average thickness, we can do this. All of them are above 1.10, right? So let me take 1.10 as the benchmark. Then this has 1 extra, 2 extra, 2 extra, 1 extra. 0.01, 0.02. I am taking all that is extra. You can add all 5 and divide by 5. I take a different approach, taking a intended average or assumed average. I take 1.10 as the assumed average. Above that, how much is there? Here you have 1, 2, 2, 1. All those additional values I have taken and divided by 5. So that's 1.10 plus, this is 2, 4, 5, 6. 0.012. 0.112 millimeter. That's the average we get. But I can't give that reading. Do you know why? We already defined the least count is 0.01 millimeter. So the reading I give, answers I give have to be multiples of 0.01 millimeter only. I can't go to the third decimal. So let's say this is approximately 0.11 millimeter. Here round it to 2 decimals and give it. 2 decimals. Clear? Because the least count is only up to second decimal. You can't go to the third decimal, which will be inappropriate. In how many decimals will you give the above calculated answer? See, even they are asking that. Explain why. So let's say 2 decimals. 2 decimals. Since the least count is 0.01 millimeter. Since the least count is 0.01 millimeter. A student suggests to immerse this plate into water and measure the volume of water displaced in order to measure the volume of the plate. This method is not accurate compared to the above mentioned method of calculating the volume using A, B and T. Explain why. Now we measure the thickness, width, length and all, and then find the volume of it. But another student suggests, why don't you take a cup of water and drop this in, see how much of water is displaced and find the measurement or find the volume. Because you know, if we immerse something into a liquid, same volume of liquid will be displaced. The immersed object's volume and displaced liquid's volume will be equal. That's what Archimedes found, right? So can't we use that idea to find the volume is what he is asking. And the statement says that is not very accurate. The reason is this. This is a very small metal plate. So the amount of water is going to displace will be very small. You may not be able to measure with accuracy the amount of water that is displaced. Right? Imagine one drop of water itself is 1 milliliter. That is 1 centimeter cube. Right? So if it is less than that, it's going to be like very small amount of water that is being displaced. Like imagine you take a cup of water and you dip a blade into that. How much of water is going to be displaced? It's a very little quantity, right? So measuring that can be difficult. So let's say, explain why the amount of water displaced will be minimal. Clear? Right. Now let's see another paper. This is from 2007. You are to determine the density of the material used to make an A4 size photocopy paper. You are provided with a spring balance, a triple beam balance and a chemical balance. which are available in a school laboratory. What is the most suitable measuring instrument that you would select to determine the mass m of the sheet of paper? If you take one sheet of paper, that might not be even a gram, right? It's going to be a very small weight. If it is something a gram or less than gram, ideally chemical balance is suitable to measure it, because even if you take a triple beam balance, you can measure in 1 gram, 1 gram, 1 gram. The least count is 1 gram. So you can measure in multiples of 1 gram only. So suppose you want to measure 0.5 gram, 0.8 gram, 0.9 gram, the triple beam balance will not help you. So therefore, and spring balance anyway won't help you. So anyway it has to be chemical balance. Chemical balance. Chemical balance. In order to determine the volume of the paper, you have to take 3 measurements. Indicate below the most suitable and appropriate measuring instrument you would use to measure each of them. Length of the paper. Length of the paper, they said 30 centimeter. 30 centimeter, you have to use the meter ruler, because vernier caliper will not have up to 30 centimeter. Vernier calipers are usually up to 15 centimeter. Right. Width of the paper, again meter ruler. Not only that, then vernier caliper, we have another issue. When you keep it in between the jaws and when you press the jaws, the paper will not remain in the same shape. Right, paper's shape can change. Therefore, it's very difficult to use it, the vernier caliper, to measure the width and length of paper. It has to be meter ruler. Thickness is very small. Even meter ruler is not enough. Vernier caliper is not enough. We have to use micrometer screw gauge. Micrometer screw gauge. We have not done the practical on micrometer screw gauge yet. In the second practical, I will show you how to use the micrometer. Yes, micrometer screw gauge. Write down an expression for the density of the material used to make the paper in terms of ml Wt. Density is mass divided by volume. Volume has to be length, width into thickness. Mass divided by volume. When measuring the thickness, it is more appropriate to take several readings at different places of the paper. What is the reason for this? Why do we have to take measurement at different places and get the average? I explained it multiple times, because the thickness may not be uniform. Thickness might differ place to place. So we take an average. Write it. Thickness may not be uniform. Thickness may not be uniform. Once the most appropriate measuring instruments are used by a student to measure L and T, the values he obtained are given below. Determine the fractional error of each of the measurements L and T. Length, we used the meter ruler for it. Meter ruler 1 millimeter, that means 0.1 centimeter is the least count. 0.1 divided by 30. We don't have to solve it. We don't have to simplify it. Thickness we measured using micrometer screw gauge, which usually has 0.1 millimeter as its least count. 0.1 millimeter means 0.01 centimeters. 0.01 centimeters, correct? In order to achieve the fractional error of T, same as that of L, a student suggested to measure thickness of a bundle of papers. How many papers does he need to make the bundle? Now see, when you measure the thickness, fractional error is 0.01 over 0.15. 0.01 over 0.15 if you measure only one paper. If you measure n number of papers, measurement is going to be 0.15 into n. Right? So fractional error will be 0.01 over 0.15 into n. And he wants it to be equal to same fractional error that you got for the other one. Which one? This one, 0.1 over 30. 0.1 over 30. So multiply here, this is, if I cut this as 1 and 10, to 0 cancel, 3, 0.15 n. N is going to be 20. So if you take 20 papers together and measure the thickness, the measurement will increase, therefore fractional error will reduce. In practice, the unit called GSM is used to measure the thickness of papers. GSM stands for grams per square meter. That is the mass of 1 meter squared area of a given paper. Right, you take 1 meter squared paper and the weight of that is what they say GSM, grams per meter squared, square meter. Assume that in A and B above, M was measured in grams and L and W were measured in centimeters. Write down the expression for GSM value of the paper. Paper GSM value, right? So GSM value will be, M is already in grams, I don't have to do anything with it. And then I need to take the area only, thickness is not required. Area L and W, L they have measured in centimeter, L is in centimeter. So multiply that by 10 to the power minus 2 to get it into meter. Width also in centimeters, multiply by 10 to the power minus 2. So this is in gram, now this is in meter. After dividing that by 100, after multiplying by 10 to the power minus 2 each, it's meter. So it becomes M into 10 to the power 4 LW. M into 10 to the power 4 LW will give you the grams per meter squared value. Right, see, very easy, straightforward questions. There is nothing complicated. So measuring equipments, measuring instruments, if you get in the exam, the questions are very easy, right? Very easy, very straightforward. Only thing you just have to know the basics. Right? If you have seen doing the experiment couple of times, you must be able to answer the questions without any problem. If they bring in something new idea like GSM they brought in here, they will explain it. You don't have to bring your own extra knowledge out of the syllabus. Anything outside the syllabus that comes in, they will bring in the idea and they will explain it to you. So just read what they say and then apply it. Next, this is 2014 paper. The following measuring instruments are given to determine the density of material of a small uniform cylindrical of the form shown in figure. A vernier caliper and electronic balance. Right. You're going to measure the density, so obviously you need the mass and the volume. When it comes to volume, I already explained. Say if let's say D1 is the external diameter, D2 is the internal diameter, H2 is the depth, H1 is the height. Pi D1 by 2 squared into H1 is the full volume minus pi D2 by 2 squared into H2 will be the volume of that carved space, the cylinder inside that. This would be the overall volume. Anyway, now what do they ask? This is not what they ask now. What do they ask? Before using a vernier caliper for taking measurements, what is the first step that you should take? Right. Find or calculate the least count and find the zero error if exists. This is the first step we have to do. We have to find the least count and then we have to find if there is a zero error. Write down an expression for the density D of material in terms of volume V and its mass M. We all know that very simple. Density is mass divided by volume. Mass divided by volume. Very straightforward. Very simple. In addition to the two measurements, that the outer diameter and inner diameter of the container, state the other measurements that you would take using the vernier caliper to determine the volume of the material, the height, external height and the internal depth. Let's say height of the container. Height of the container. Internal depth of the container. Next, The figures 1 to 5 show below all the relevant positions of the main and vernier scales pertaining to one set of measurements that has been taken in order to determine the volume of the material of the container. Relevant jaws or depth rod, etc., that have been used to take each measurement are shown on the right hand side of the figure. Note, height of the container is greater than its outer diameter, the external diameter. Height is bigger, right? Okay, 5 different positions of the vernier and the jaws they have given. Identify the figures correctly and relate them to the measurements that have been indicated in C and fill in the table given below. Wait, before we go to the table, let's try to understand. Can you see here the jaws are closed? So basically they are trying to identify the zero error. This is about zero error. So we'll just make a rough note for us. And then look at the second one and last one. They are using the external jaws, outer jaws. External jaws can be used here to measure the outer diameter as well as height. The bigger value must be height because they said height is bigger. This is like 2 centimeter. This is like 3.5 centimeter something. So this is where you have the bigger value. This is for height. This is for outer diameter. Outer diameter. Here they have used the internal jaws. Internal jaws are for inner diameter. Internal diameter. Here they have taken the depth probe or the rod. This is for the depth. Clear? Right? We have to identify that first. Then we will go to the table. Reading of the vernier caliper in the first case. Can you see which one is aligned? The second line of the vernier is aligned with it. That means 2 into 0.01. 2 into 0.1, isn't it? Vernier caliper least count is 0.1 millimeter. So 2 into 0.1, 0.2 millimeter. There is nothing called correct reading because this is about zero error. Other readings we have to adjust for this zero error. Second one. The reading is, can you see again the second line? So 2 centimeter finished. Right? 0 of vernier is right after 2 centimeter. That means 20 millimeter plus 2 vernier scales. 20.2. Adjust for this 0.2 millimeter. That will be 20 millimeter. Subtract the error. What is this? This is outer diameter or external diameter. Outer diameter. Correct? Then third one. This is at 15. Which one is aligned here? Not 15, 16. See, can you see? After 16 only the 0 comes. Vernier 0 comes after 16 and then the second one is there. So 16.2. 16 divisions of main scale and 2 divisions of vernier scale. 16.2. 0.2 has to be subtracted. Error 16 millimeter. What's that? Inner diameter. Inner diameter. Third one, 30 centimeter and again the second one. Main scale 30 divisions, 3 centimeter means 30 millimeter rather. 30 millimeter and the second point. So 30.2. Subtract 0.2, it's going to be 30 millimeter. It's very simple, very simple. And what was it? It was the depth. The internal depth of it. Last one, 35. So 35 millimeter and see this one, 1, 2, 3, 4. Fourth one, 35 in the main scale and fourth one, 35.4 millimeter. Subtract the error, it has to be 35.2. This is what? Height of it. Height of the container. Clear? Right. Write down an expression for the volume V of the material in terms of the symbols x1, x2, x3, x4. Already we wrote it earlier, but not in x1, x2, x3, x4. Let's say V will be pi. What is the external diameter? outer diameter is x1. x1 by 2 squared into what's the height? Height is x4. So this is the full volume minus what has been carved out from that. x2 is the internal diameter into x3. x3 is the depth. Clear? If you want, you can take the pi out, or we can just keep it like this, or even 4 out, however. x1 squared x4, x2 squared x3. Correct? Using the expression written under E1 above and readings that have given in the above table, calculate V. V is going to be pi is 3, they say. x1 was 20 millimeter, x4 35.2. 20 squared into 35.2. We had a 4 here, right? Minus x2 squared and x3, 16 squared 30. 16 squared and 30. How do we solve it? I'll take this 4 inside. Look at this. This is going to be 20 squared is 400. 400 divided by this 4, it's going to be 100. So 35.2 into 100, 3520. Minus 16 squared means 16 into 16. Divide by 4, it becomes 16 into 4. 16 into 4 is 64. 64 into 30. 0, 3, 4, 12, 1, 18, 19. 3 into, this is going to be 1600. So that is 4800. Be careful on the units. Millimeter cube, because we wrote everything in millimeters. Millimeter cube is the volume we get, which you can say 4800 into 10 to the power minus 9 meter cube. Why minus 9? 1 millimeter is 10 to the power minus 3. So millimeter cube means 10 to the power minus 3 cube, which is 10 to the power 9. 4.8 into 10 to the power minus 6 meter cube. 4.8 into 10 to the power minus 6 meter cube. According to the reading of the electronic balance, if the mass of container is 9.6 grams, find the density. Easy, but density in that unit. So 9.6 grams kilogram. This already we have found in meter cube. 4.8 into 10 to the power minus 6 meter cube. 4.8, 9.6 is 2. This goes up 10 to the power 3. 2000 kilogram meter minus 3. Can you see? So simple, straightforward calculations. There is nothing complicated. Right? Only thing you just have to know certain parts of it and how to use each part of it. Right? Very straightforward question that you get from experiments. You have to watch while doing the experiment couple of times. Each explanation we give you need to remember, and what you get in the structure question is almost straightforward questions. 20 marks for 4 structured essay type questions, you get 20 marks. That 20 marks actually you can try to get fully. Without losing a single mark, you can get that 20 if you study this carefully. We are going to do all the experiments in the list and show you. Clear? Right. So that's all in this experiment. The 4 past paper questions that have come on this vernier caliper I have shown you. So that's the first measuring instrument you had. After this, we have to take micrometer screw gauge, practice this and come to the second experiment. In that we will be seeing how to use a micrometer screw gauge.